All right, let's continue his line of thinking here, because he was testing out his inverse square law with known quantities to really see if it makes sense what he was saying. So he said this holds, as we see saw in the last video, isn't it? He was trying to test out his inverse square law. So now he then considered a situation where this planet was right there at the Earth's surface. When it's right there at the Earth's surface, the force that you'll be considering will be weight, because it will be at the Earth's surface. So it will be weight, which will be now mg. This F will now be equal to mg, and the radius will be equal to radius of Earth only, not the radius of orbit like this. No, it will just be the radius of Earth, because the object is now at the surface of Earth. It's now right there at the surface of Earth. So the radius that we're considering is the radius of the Earth only. We're not considering the radius of orbit, because there's no orbit radius. The object is now at the surface of the Earth. So this will be the radius of the Earth, because it's at the surface. So in that case, he then said, for getting a ratio like this, 4 pi r, this force here that is there where the object is, as to mg, the force where it's at the Earth's surface, this ratio should also be equal to the ratio of the what, of the radii. If the inverse square law holds, it should be equal to the ratio of the radii if the inverse square law, his inverse square law holds, this being the radius of the Earth squared, and this being just the radius of what, just being the radius of the orbit, which is what, consistent with this force, this mg consistent with this radius. So that's what he discovered. Then he divided the forces. When he divided the forces, he divided also the radii. So this one is going to be 4 pi squared mr over t squared divided by mg. So we are going to put mg at the bottom, should be equal to 1 over r squared divided by 1 over re squared. That's what he did, isn't it? This one will cancel, this one will cancel, and therefore, and then he made g the subject of the formula, because he wanted to see, but the g was known. This small g was the acceleration due to gravity. It was known at that time. So he wanted to see if his calculation using the inverse square law will give the g that is close to the known g. If it is, then it means this assumption here, it has been proved twice. It is known. The first time was being proved that what, it's consistent with Kepler's third law. So he made g the subject of the formula, and he got 4 pi squared r squared all over, oh no, r cubed, yeah, it's supposed to be r cubed all over r squared t squared, like this. So this r this big R that I just put, I noticed that I then just took the big R from nowhere. It's supposed to be here, the big R representing the radius of orbit of the moon, right there where it is, far from the what, from the Earth. So that's that big R. This is this big R. I didn't want to confuse it with small re, which is just the radius of Earth when the object is now considered to be at the surface of the Earth. So that is what it is. So now here, this was known, it had been calculated. This had been calculated. The period of the Earth, of the moon around Earth had been calculated. So he put what? He put these values in there, and he was happy when he discovered a what? When he got a g that is very close to what? When he got a g that is very close to 9.8 meters per second squared, which means his inverse square law mathematically also what? Was also proved, which means it was correct that the force, he then saw that the inverse square law, like the force of attraction between two masses, the force of attraction between two masses is inversely proportional to the square of their distance apart. If the distance is r, then the force of attraction between them is inversely proportional to the square of the distance apart. He saw that this one had been proved. So now he set out to get a law that anyone can use, a formula that anyone can use, because his law had been, his assumption had been proved that his assumption was correct. So he now just needed a formula that anyone can use at any time in his sleep, on wherever the person is. The person just needed a formula they could use. So he then went on to find the gravitational constant. You remember his formula? His formula was F is equal to K m over r squared. So he needed to find this K, that if he tells people what K is, it's just a matter of someone saying, okay, I'm calculating mass, I'm calculating the force of gravity on a mass of 2 kgs, that is at 1 million kilometers from the Earth. Then they could, with a universal K, a K that doesn't change, a constant that doesn't change, this gravitational constant, then someone would have been able to calculate force. So he set out to now calculate this K. What Newton realized, because he was a genius, what he realized was that the force of gravity on an object not only depends on the distance, but also on the object's mass in a direct proportion. That's what we discussed, isn't it? And due to his third law of motion, now with this third law of motion says, if you push this body with a force of 5 newtons, this body will push back on you with a force of 5 newtons, because for every action there's an equal and opposite reaction. That's his third law of motion, if you remember well. So with that he was like, but if the earth if this earth here, earth at the center, if the earth is attracting the moon with a force FSM, isn't it? Then also the moon is attracting the earth with a force that is equal and opposite, FMS, which means if there is okay, now I put S, so let's call it the sun. If this is the sun and this is the moon, so if the sun is attracting the moon with a force FSM, it basically means the moon is also attracting the sun with an equal and opposite force, because for every action there's an equal and opposite reaction. So due to his third law of motion, when the earth exerts its gravitational force on the moon, when the earth exerts its gravitational force on the moon and it's pulling the moon exerts an equal and opposite force on the earth. Due to this symmetry, he reasoned that the magnitude of force of gravity must be proportional to both masses. So he then reasoned out that it's not only proportional to mass of the moon, it's also proportional to mass of the earth, of the other body, that the force of attraction is proportional to both masses. It's proportional to both masses. If the mass of the earth increases, the force will also increase. So he reasoned this out from his equal and opposite reaction law number 3. So together, putting it into his assumption, he then said F is equal to K, mass of, let's say, mass of earth times mass of moon all over r squared. That was his new development. Which makes sense if you are following this video. It does make sense. So now Newton still had the problem of calculating what? This G. So he set out to what? To calculate that universal gravitational constant. Okay, I just called it G because that's the convention. It then later changed from a K to what? To a G. But for now, let's just call it K, just for consistency's sake. So now he needed to calculate this K. Many experiments were done that are difficult for me to explain on a video right now, but experiments were done by a guy called Cavendish. Cavendish did many experiments to measure this K, to see the force. I think it was Cavendish and Boys. Yeah, Cavendish and Boys. They did experiments to measure this K. And I told you this K then later changed to a G, just a universal gravity constant. It was just the same constant, but for it to look prettier and just to be consistent, it was just changed to a G. So this G, called the universal gravitational constant, was measured by Cavendish and Boys in experiments, and they found that G was approximately equal to 6.67 times 10 to the power of minus 11 Newton meter squared per kg squared. That was the value of G after they calculated it. And it became a universal gravity constant, which means with this value, when you know the mass of one object and the mass of another object divided by r squared, you can calculate the force of attraction between any two bodies. So right now, if you're sitting next to someone, if you know the mass of that person and the mass of and your mass and the distance between the two of you, the force of attraction between the two of you will be calculated using this and this gravity constant. But you notice that it will be very, 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 very minimal due to this -11. You need large values of these two masses to come up with a noticeable force. But you probably are weighing 60 kgs, the other person may be 70 kgs. They will not be able to neutralize this -11. That's why we do not collide, or we don't get attracted to each other in a noticeable manner. But the force is there. It's difficult to measure because of this -11. You can calculate it. Put 70 kgs there, put 80 kgs there. The distance between you probably 1 meter. Just put 1 meter squared here, and you see that the force is not noticeable. It will be minus something. So yeah, this became his universe. So this one was what? This was his new law of gravitation. This is called Newton's universal law of gravitation. That's the point that we wanted to get to. So it took him years for him to get to this point. It took him years and many experiments for him to get to this point. For him to get this G, it took him a lot of time, and the Cavendish and boys had to come in to get the right value. So now, this is what we will be using when we're calculating force of gravity. It basically means, in words, it means every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses. Directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. This force acts along the line joining the two particles. If the two particles are like this, the force of attraction will be on the line joining the two particles. So the force of this particle, the force on this particle due to this particle will be here, and the force of on this particle due to this one will be on that side, and they are equal and opposite due to Newton's third law of motion. In the next video, in the next couple of videos, we are now going to get into examples to see how to best apply this and put all the principles together. So